So the talk is Explainable Machine Learning for Trustworthy AI. And actually the combination of the two talks together are fantastic because I will repeat some of the things, but many of the motivational things have already been highlighted by Carlos. So I think the two together, I think will provide the big picture on explainable machine learning nowadays. So the work that I'm presenting, it's the result of many colleagues that are participating to this project, ERC project on explainable AI, which is aimed at creating science and technology for the explanation of decision making. Now we are starting our third year, and so many of the talks of the arguments of the today talks will be related to the achievements, current status of the projects. So just a small reminder. So it's explainable AI is not a novel topic. So it has been a very interesting area since the last 20 years. It has and in many different AI fields. So you can find methods and proposals in planning, in search, game theory, machine learning, user interfaces, robotics, so natural language process. So and it is really an old topic looking still for excellent solutions. So as Carlos was saying before, so one of the underlying issues is that what is an explanation, and what is a good explanation, and for who. Exactly as Carlos was saying, there might be different interests in having explanations. So the end users, the engineers, the data scientists that has created the system, the regulators. So I mean, one of the very starting point of explainable AI is that, okay, we have in front of us different possible stakeholders with different interests. So, and for sure, a good explainer should model the user background, should have in mind who is the final user. This is something which is really in the background of any of the new XI tools. So who is the end user? What are the motivations, and how to interact with? We'll see. And another important point is that there are other motivations for explanation. Is the fact that there is GDPR, of course, that is in some sense expressing, regulating the right of explanations for people which are when automated decisions are considered. But also there is also this consideration that the artificial intelligence that we want to have, it's an artificial intelligence which is meant for humans to improve the ability and the happiness possibly of humans. So we want to design systems that do not harm, that incorporate ethical values, and so that can empower humans with extra tools, but within a set of values that are socially accepted. And among the various values, its explicability is one important pillars of this vision of human-centered AI. And it is an important pillar in a double sense, in the sense of explaining the rationale behind the decisions, but also explaining who is responsible for what. So those two dimensions are fundamental, and you will see that explaining machine learning, so equipping machine learning with methods for explaining, it's useful for achieving a sort of also for accountability, for supporting some of the values that we would like to inject in our novel artificial intelligence. So first of all, but what is an explanation? This is a very old questions. Even Aristotle was asking this. So there might be an explanation. So that an explanation might be an example or a story or some mathematical representation. So again, the game is that who is meant for who is meant the explanation. So just to give you an idea of what is the panorama so far of the explanation that we have. So explanation may be highlighting what the properties of the features and the contribution that and the relevance for that had these features in the learning process, the learning process that brought to that specific decision or to overall or maybe the saliency map, as were in the previous talk mentioned several times. So the saliency maps, again, where the space, the input space are the pixels of the image. And this is another important point. In this panorama of the explanations, what is the type of data we are talking? It's very much relevant, because depending by the type of data, we may do things, several different things. So with images, the saliency maps highlights which are the pixels which contributed more to a certain decision. So we predict this image, it's a Janko bird, and then you can see how in this comparison, the comparison of how several algorithms, saliency maps computed by several algorithms, how they differently behave. This is an idea of why we still do not have a uniform answer. What is the so there is still a lot of research to do. In the case of text, there might be highlighting the keywords that particularly contributed to that prediction. So it's imagine a text that has been relevant to recommend a movie. So why I recommended that movie to that users, and then you highlight from the test which have been the keywords which were particularly relevant by the model, which was behind, used by the model behind. Or maybe an explanation, maybe in terms of prototypes, subportions of an image in this case, which are correspond to different sub subpart of the image, which were particularly significant with respect the images which were in the training set. Or explanation as a narrative, where the explanation it's increased as with adding argumentation or adding other sources of text which can enrich the explanation with a sort of narrative, also possibly using other knowledge from a knowledge graph or from other sources. Or explanation as a counterfactual. Carlos mentioned them before, and you'll see later on. So you explain how your loan is being rejected because those features were too high, the following features were too low, and the following features require changes. You can show also a sort of supporting a sort of what if reasoning, what you can do, what if you change something, and where you will end up. Okay, and that's the beginning of the story. So in our project, we think that explainable AI it's an important element also for preserving and expanding human autonomy. So putting the users in condition of understanding why certain decision has been produced, it put the users in condition not to demand to an algorithm, so reducing its critical capacities from one side, or even for gaining trust. So if you do not demand, but you may argue with the algorithm. So and if you understand, you may have argument to counter debate. So essentially, what the goals of the project were, so empower individuals against undecided effect. Again, if you understand, you can understand. As was said before, the previous talk, explanation may be used for planning different or designing scientific experiment, but also for discovering bias or discovering discriminations, to implement the right of explanations, to help people to do better decisions, to preserve and expand the human autonomy, and with the particular focus, so what I call the Dr. House model, the fiction that I imagine that many of you knew. So explanation so what is the Dr. House model? So Dr. House is a very intelligent agent which collaborates with other intelligent agents. Those other intelligent agents challenge him with a new hypothesis, bring new knowledge, so discuss and argument with him. At the very end, the responsibility of the decision is in the hand of the Dr. House. So this is what we would like to implement in our project. So explanations as a human-machine conversation, where you can provide, the machine is capable of providing different forms of explanations in terms of also some background knowledge of the users, but the users may react asking for, so you provide the why, the system provide why a certain decision, so you ask for a decision for this image, so and then the system provide a recommendation, a decision, then the user, the human, can ask why, and then the explanation is a sort of a logic rules or a narrative, one of the things that I said before, and they say okay, and then can be so the rules can be transformed in a narrative, but again the user can ask further questions. So what about other examples, similar instances or dissimilar instances? So you start to see that there is something that is strange. So all the instances are the same colors. So it's not that there is a sort of bias for the colors. So what happens if you do not consider, for example, some of the features, so that and again, and if you consider only the color, so you concentrate only on that features, and you discover that that features, it's the one which is particularly relevant. So you see here, but and then you can continue to ask, of course, and then this is very basic conversation. So this is what we would like to achieve. And in the project we have different lines. One is studying algorithms and models for explainable AI, and I will concentrate on this line language for expressing explanations in terms of expressive rules, statistical, causal interpretation, counterfactuals, and then there are other lines which are a watchdog platform for creating a sort of common ground for researchers and for comparing their algorithms on different domains. And we are almost at the very end of this watchdog platform. We hope that the scientific community can contribute furtherly to have a sort of a playground for people, researchers working on explainable AI, and of course use cases aimed at studying, and not only for validating our system, that is very important, but also studying the mental models of human decision making. So many of our use cases involve humans, to the aim of understanding the decision process. And finally, there are also some other important research questions, so that we are studying explanations, but there might be interplay between some of explanation and some of the other ethical values that we would like to have in an AI system. For example, privacy. So may an explanation invade privacy? So what else? So I will concentrate on the first two. But what I want to say is something which also connect with Carlo was saying, and also come from another important project which is going from in the DARPA. So what we are doing with explainable AI, we are essentially putting in place a new, a novel machine learning process, which is not, which has learning from data, and then you learn from data, and then there is also the learning of the explanators, so that and during this, when you design and learn a model, you have also to learn the explainable model and the explanation interface. That means there is then the task asked to the users will be asked to the explainable model, which is one of the plenty of the models which are produced which are produced by current literature, so post-hoc or transparent by design. And then you have this explanation interface with the user that provide the narrative, provide the interaction, and in a sort of very tight connection, explainable model and explainable interface. And of course, so this model, from one side, you need to understand the machine learning. From the other side, you need to understand the user. So that is important also to having psychology of explanation. So being capable of understanding, using the psychological theories for understanding the decision process. So, and our project is very much adheres to this idea. So just concentrating on the algorithms and models that we have for explainable machine learning. So there are those two big families that are nowadays very well recognized. So what we call explanation by design problem. That means that given a data set of training decision records, so how to develop so data, so training data where I have labeled the data. So those are already, it's an history of decisions already taken from which we want to learn, to want to construct a model which is capable of taking and recommending the decision by itself. So, and how to develop a machine learning decision model together with its explanations. So, and there is a lot of challenges there. So plenty of activities, and then there is also some activities try to go in the Latent space, doing things in a more sophisticated and simple, both together space. And the other is the black box explanation problem. So given the decision record produced by an opaque decision model, so how to reconstruct an explanation for it. So you stay with the black box, and you want to equip such black box with an explanator. So uh, um, and there are again several interesting research challenges. Again, Latent space may have a role here as well. So the reconciliation between neural symbolic it's another step, and of course causal reasoning is another important issues there as well. So this is a pictorial representation of the area. So here you can see the sort of a hierarchy of problems. So open the black box from, or you go directly transparent box design, you go by design, or you open you want to explain a black box. And here there are several approaches. So you want to formulate a sort of surrogate model which completely replace, is capable of mimic the black box, or you stay in a local in the context of local explanations. So you stay with the fact that for each single recommendation, you try to explain that specific and the individual explanations. And then, of course, there are methods for model inspection, like the saliency maps, which try to to help the designer in understanding the behavior of the system. Okay, so now I will try to give you an overview what is the done in the post-hoc explanation methods, in particular what we have done in the XI project that we are working on, with the goal of giving you an hint how this technology is working. So, okay, post-hoc explanations, and then I will talk about something about the counterfactual. So the idea of post-hoc local post-hoc explanation is that the fact that your training set where the model has been trained, what is the space of your decisions may be very complex. You see here there is the border, the pink and the blue. It's where the two kind of, this is the space of the decisions where the two kind of decisions may can, okay, of course the neural network, so the deep learning model has tried to learn this complex border as much as possible, as much accurate as possible, and maybe very complicated to reproduce such model without so the local explanation methods, essentially what they do, like they say, okay, I want to explain, I have this recommendation. So given this point here, my black box has provided, I say that it is pink. No, what I can try to do essentially, I can try to explain what is the border around this locally to this point. And in this case, probably locally is much easier. So to separate locally, maybe not a complex border, but something which is much more simpler. So this idea was firstly introduced by Lime in 2016. Essentially, all these local model explainers, how they work, simply given the point to be explained, they generate a neighborhood around the point till they have enough points, positive or negative, labeled. And the way they label, so generate the points, and then they ask to the black box to provide the label. So once they have enough positive and negative, if it is binary learning neighborhood, so out of this smaller you have a smaller training set labeled by the black box, and then you can provide a sort of surrogate, so transparent surrogate model. In this case, for Lime, the model is a regressor, and you can see the features and the explanation. It's in case of the feature relevance. In case of the image, you see the pixels, so the pixel, why the pixel being capable, is a cat for the green component of the image contributed to cat, the red ones do not contribute, it's make it farther from the decision of being a cat. So the green are for the cat, and then same for the linear regression. So what we made in our proposal, it's LORE, it's local rule-based explanations, with the idea that we want to produce logic rules. We want to produce as an explanation of local explanations. We want to produce a decision tree. So we had a different way to generate the neighborhood. So we used a different algorithm for generating the neighborhood. And once we have enough, again, same as a line before, once we have enough points in a neighborhood, we produced a decision tree. And also, and this is our peculiarity, rule-based and counterfactuals. So in our case, an example, so we have this point to explain, we generated with the genetic algorithm several points. And so we have, this is the point, age 22, income 800, jobs clerk, the point to be explained, generation of the neighborhood, positive and negative. Once we have, and the positive and negative, it's labeled by the black box. It's a sort of auditing the black box, and then we, this is the genetic algorithm, how it works. That, then after that we learn a decision tree, and then from the decision tree we provide the explanations, the rules, and also the counterfactuals. So your age, you have been denied because of your age was less than 25, jobs clerk, income 900, and you could have been a different outcome if you may increase the outcome, the income, and or if your age, keeping the age, same age, your job, you change the job. Of course, the counterfactual is an important and different task, and difficult task. So that, first of all, not all the counterfactuals are meaningful. So we have to select which are the very relevant one, the usable one, because you cannot change, for example, your age. You cannot change how tall you are. So there are some changes that may be useful, and of course we want to offer counterfactuals that expose the minimal change that you are to you, so that to you, and then so that you may explore those minimal changes. And another important idea that we have using this genetic algorithm instead of the random in the generating the neighborhood, because when you generate a random, you cover a wider space, and it is a bit more difficult to characterize the border, even in the smaller space. While with the genetic algorithm, the points are much closer, and maybe you need more time before you have enough positive and negative points. There are extreme situations where we work worst. Some in general, we work better. So that was an improvement of the Lime. And then just to get, so why counterfactual it's are important, as Carlos mentioned it before. So counterfactual are a way that they express the situation. If X had not occurred, Y would not have occurred. So it's a sort of express as a sort of causal situations. And thinking in terms of counterfactual, so require activate in the users an imagination versus a hypothetical reality that contradicts the observed fact. In some sense, activate more your cognitive process that simply exposing the factor. So there is a nice position from Ruth Byrne that I like very much, that say people create counterfactual alternatives to reality when they imagine how things would have turned out differently, if only, especially after bad events. So, and this is evidence of human reasoning works. So, and of course, so um, it's a first step towards expressing in terms of causal reasoning. Um, and of course, as I was saying before, it has to describe the smallest change to the features that changes the prediction to a predefined output. So in our, just to give you an example of how LoRa produce, if this is this is we are on the Compass dataset. I'm sure you know the Compass dataset for predicting recidivism of people in jail, a system which was used by in US for supporting judges in some evaluation process. So given those features of the person to be evaluated, and then the black box provide high risk of recidivism. So the Lore will return the motivations in terms of features, simply the logical rules. So age less than 25 days before the arrest, such that, and then several possible counterfactuals that might provide alternatives, way to have a different prediction. This is a comparison, for example, with Anchor, a version of Lime for relational data, which is and you can see that the kind of fragmentation of in the space of features is much higher, because of course in this game of various methods of for explanations, there are also metrics for evaluating the the quality of the explanation. So I mean, the explanations shouldn't require an enormous effort in comprehensions by the user. So the length, so there's a variety of different methods, even though we are not yet at the ideal metrics. And then, of course, SHAP, in this case, SHAP is another method which can be used locally, also globally. It comes from game theory. And it says that the major contributions to the such high prediction, black box equal to high, is that age has contributed very negatively as 0.0.7. So this is the explanation of SHAP. And then okay, this is the explanation, for example, of another method. You see the variety of proposals which are in literature. So why it is important also metrics for evaluating the comparison. On image, again, on image, what is producing LoRa? In image for as counterfactual, instead of counterfactual, is also produces counter examples. So in the case of image, for example, thanks to the segmentations, as several other methods do, it can say that, so the black box has predicted this image as 9, and then you can see that which are the contributions, so Lauren will say these segments, if of the image particularly contributed to 9, but instead, if there wasn't the segment as 6, that image would have been 4. If there wasn't the segment 8, that image would have been 6. So this is just to help you in trying to see how contrastative, we can say contrastative reasoning may be very helpful, not only in highlighting in the image which are the salient portion, but also saying what might be different. We also used Lore, this idea of why and why not in the sequential data with but in that case using ontology, an ontology in the case of medical, we have this Dr. XI, medical ontology for both for generating the neighborhood and also for generating the explanations, in order to provide the factual and the counterfactual in the language of the physicians. Another type of data on which we so there is another approach. It's trying to use I mean, of course, when you try to do factual counterfactual on the high feature space, maybe very complex and it's not very informative. So we try to experiment another approach, trying to go up in the latent space, essentially with high feature data. We try to go to reduce the space of the features using the encoding autoencoder technology. In the autoencoder technology, going in a simplified space. In that simplified space, using again this capacity of going back and forward by the latent space with encoder and decoding functions. So we might generate a factual and counterfactual, a decision tree for having factual and counterfactual in the latent space. Again, using the function for coming back to the real data, auditing the black box, labeling the black box, going back in the latent space, generating a labeled neighborhood in the latent space, learning the decision tree in the latent space, and generating rule and counterfactual rules in the latent space. Now you can use these rules and rules and counterfactual rules learned in the latent space as filters for generating exemplars in the latent space, picking up exemplars in the latent space and transforming them with the decoding functions in the real data, so that we have improved a lot our capacity of explaining images and generating exemplars and counter exemplars. So for the given that image that the black box has predicted to be 9, so essentially we generate the saliency map, and that's similar to those the others are doing, but we are capable of generating exemplars which explain why that image was, what are the exemplars that contributed, which are similar to that prediction, and also the counter exemplars. You see that, so those 3 images are the exemplars, and 4 and 7 images, which are much closer to 4 and 7 as a counter exemplars. Same method. So we made on another kind of another kind of complex data, which are the time series. Again, with this idea of going transforming the complexity of the time series in a reduced space, latest, again in this adversarial autoencoding. I remember you that these techniques allow you to learn the identical function plus learning also the distribution, so that you have also generators. That's why you are capable of generating the exemplars. So, and this is, for example, a time series for the sounds of a bell, and then you generate many positive exemplars, which are for the bell, similar to bell, a lot of counter exemplars which differs from bells. You see that which have a different shape. Those are synthetically generated in the latent space and then transformed in time series in the real space to provide exemplar and counter exemplars. And that out of that you can further elaborate the explanation so what we are producing as a first format of explanation. Then you can elaborate more, and then you can produce, for example, a shapelet, factual rules in terms of shapelet. And you'll have you say that this is a bell because it contains the shapelet 1 and the shapelet 2 and does not contain the shapelet 7. So, and you can express in a sort of again logic rule. So now just to very fast to go back, I think we have 3 minutes only. I want to go to so there is the other line, transparent box by design, which is also very interesting side. So one example is the one that I was showing before by Cintia Rudin, by providing prototypes, and the prototypes are learning are learned layer by layer during the training phase, so that when in the test phase, those prototypes which are learned, they sort of the test phase, it's against the prototypes. You don't even do anymore the model. So another interesting line on this transparent by design is trying to match layer by layer to the concept that you find layer by layer with some concept with exist in a knowledge graph. So augmenting the intermediate features with more semantics, such that knowledge graph embeddings or entities. That's another very promising line. Of course, the issues are how to do this knowledge matching between the neural network and the knowledge graph. And of course, even here, there is this idea of interaction of explanations. Now, I go very fast now. So another issue is how, so the explanation is produced by those models are just the raw level of explanation. Then you have to build the language, which is the language to express such explanation, going closer to the users. So one lines that you are trying to follow by the many local explanators that you can produce, you can generate a global explanations. And here is so you have a set, essentially you generate a lot of local explanations through the something like Lore, for example, which provide logic rule, and then you start to combine the rules in a different way, such that you can generalize from rules and having again a global model out of the many local. Let me finish. The goal is, as one that I say before, explanation as a human machine conversation. For doing this, we have to also to be capable of going towards the users, understanding models for human decision makers. So also this can be done with plenty of social experiment, controlled trials with prediction explanations. Let me say the very last thing that essentially what we are doing now, we are what we're doing with artificial intelligence, it's designing socio-technical systems so that we cannot stay anymore with the standard methods for evaluating a system. We have to go behind the Turing test. We have to evaluate the quality of the entire decision, which also implies the humans in the loop. Because once we propose the decisions, the decision maker may change his mind. So we have to imagine a completely different way to evaluate and validate, and this implies different disciplines. As I was saying before, XI is a combination really of different. Implies social science, human-computer interaction, artificial intelligence. So this is, sorry, so conclude my presentation. This is the work done by many people, I was saying, but it's also interacting with in many projects that we are working on, trying to involve several community at the European levels on this topic.